Greetings and welcome back. Today we'll be talking about resonance. Resonance should be a term that you remember from general chemistry, but if not, that's okay. The goal of resonance is to talk about moving charges around within a molecule, which is going to have the net effect of making that molecule more stable. The first example I'd like to look at is sodium bicarbonate, or NaHCO3. Anytime we see the sodium in organic chemistry, it is an Na plus, and the rest of that molecule must be minus. So it's an HCO3 minus. Anytime you see something like a CO3 or a PO3 or an SO4 or something like that, the carbon is in the center, and the rest of the atoms are around it. So CO3 is going to look like this. Those oxygens on the right and the left need one more bond, so we'll give one of them a hydrogen. The other is going to have that minus charge, and therefore an extra electron, which gives it a third lone pair. So this is sodium bicarbonate, and what we have drawn down here in a Lewis structure is the bicarbonate ion. All right, the bicarbonate ion has a resonance structure wherein we can move that minus charge somewhere else. So let's practice drawing our electron motion arrows to show where those electrons could possibly go. So the logic of this starts with the fact that that O minus has too many electrons, and what it wants to do is give some away. It can't just take electrons and push them anywhere else and just give them to someone else. Instead, the only thing you can do to a lone pair in terms of electron motion is to share it. So this oxygen could take one of its lone pairs and share it with its neighboring carbon, which would make a brand new double bond right there. However, if you just stopped there, imagine you'd have a double bond here. That would be 5 bonds to this carbon. So at the same time, this carbon, in order to have meet the octet rule, has to unshare a pair of electrons. So it unshare this pair of electrons right here and kick it up to the O. That would result in another version of this molecule, which would have now a third lone pair on that top oxygen, and thus a minus charge, and a new lone pair on that oxygen to the right. These are two different structures for the same exact molecule. They look very similar, except that from this oxygen's point of view, he's less stable here because he has a minus charge, and he's more stable here because he's neutral. For that top oxygen, it's more stable here because it's neutral, less stable here because it has a minus charge. And so, in effect, what we have done is spread out or delocalized that charge. Really, it doesn't go back and forth, but what the actual molecule looks like is somewhere in between those two. We're not going to do this very much, but you can imagine that halfway in between those things would look kind of like this. And I'll say minus 1/2 here, and minus 1/2 there. If you average everything out, this is really what that molecule looks like. However, we don't really deal with half bonds and we don't really deal with half charges very well. So instead, in organic chemistry, we draw resonance structures, which indicates that the molecule acts something like this and also something like that. The point is that in resonance structures, we're never breaking single bonds. Therefore, in resonance structures, the only ways that we can move electrons is by sharing lone pairs or pi bonds. Pi bonds, if you remember, are the second half of a double bond. So we take this double bond right here, and we move away the pi part of it, leaving the sigma. The sigma framework, and remember, every type of bond has a sigma bond, those guys are stuck. If we break any of those sigma bonds, we're breaking the molecule up. That would be a reaction. It's not resonance. So resonance is just where we move lone pairs and pi bonds within a molecule to give us kind of a new version of that molecule in which the lone pairs have moved around or the double bonds have moved around, so it gives us usually a new location for a charge. And because each of these oxygens is only shouldering half the load, each of these guys are minus 1/2 instead of being a full minus, it ends up giving you a much more stable molecule. So let's look at some more examples. All right, so our first example is going to look like this. We will have a C+, and a C+ doesn't have a full octet. So I would like you to see if you can move electrons around in order to give a second or another version of this molecule, basically where the charge has moved. All right, so let's see how this could happen. That C+ doesn't have enough electrons, and in resonance structures, the only things you can move are double bonds, that is to say pi bonds, or lone pairs. The only thing we have here that we could move is this lone pair right here. So what we can do is take this lone pair and share it in this direction. That would give the carbon on the left a full octet, and it would give us a brand new molecule. Well, it's not a really new molecule. It's just another way of considering the same molecule. And now the plus charge would be on the nitrogen, because the nitrogen now has four bonds and no lone pairs. That's it. These are the only two possible resonance structures of this molecule. So let's try that again. Here is another molecule. We're going to put a minus charge on that carbon. And I'm going to put that right next to a ketone. So see if you can figure out how to move those electrons around so that you end up with a charge in a different location. All right, so what we can do is we can take that lone pair, because this carbon has too many electrons, and we can share it. It's the only thing we can do to a lone pair is share it. So we can push it over here. And just like with sodium bicarbonate, that's a trend we'll see a lot. If you put a double bond here, this carbon would then have 5 bonds. So it needs to unshare electrons. The only way to do that is to kick some up to that O. And so the result of that would be this carbon on the left would still have 2 hydrogens, but now it has a double bond. And instead of having a double bond O, we push some of those electrons away, and so therefore it only has a single bond O, but that O has a new lone pair. All right, so that's the resonance structures of that guy. Let's try one more here. This is going to be very similar, only bigger. We'll put a CH3 followed by a C-. I'll stick an alkene in here. And an aldehyde. All right, so I'd like you to actually draw this on your paper, if you have paper. If not, find some, or write on your desk, or tattoo on your arm, or whatever you want to do. But see if you can figure out, in this case, there are going to be 2 good resonance structures of this molecule. See what you can come up with. All right, so I never want you to just start willy-nilly. The idea here is that we're spreading charges out, and the way to do that is always to move electrons away from a minus charge, because a minus charge means they have too many electrons. To make themselves neutral, they need to share their electrons. Or we can pull electrons towards a C+ so that that carbon ends up being neutral. Anytime you have a plus charge, you want to go towards the formally charged neutral state, and so we move electrons in any way that we can, again within those 3 methods that we have already, in order to make things neutral. All right, so in this case, we can start off by taking that lone pair and moving it away from the minus charge. If we stopped there, we would have a double bond here, and so this carbon would have 5 bonds. So it needs to unshare. So let's just push that up there. So that would give me a resonance structure that had a new double bond off of that second carbon from the left, and a new lone pair on the 4th carbon, so that would be a C-. At this point, it looks a lot like the molecule above, where we can take that C-, share it down this direction, move that pi bond up here. That would give us another structure in which, I'm going to turn this into a line angle just because I can. We have an O- up here. It's not best to do this in line angles, but I was kind of running out of space on the slide. So you can see that in this case, the minus charge is spread out between 3 locations. This carbon right here, this carbon right here, and this oxygen. And you can know that by drawing all of the resonance structures. So resonance structures are something really important to practice. So instead of giving you a bunch more examples, I'd like you to stop right now and just go practice. Thank you very much, and I will see you in class.